Hi and welcome to part 3 of this lecture. In this part we're going to talk about the function blocks enabling, decoding and selecting, and that's going to provide the groundwork for talking about multiplexers in the next part. So enabling functions are really useful in design. Corresponding to each of the functions is a combinational circuit implementation called a function block. Historically, these function blocks have been packaged as small-scale integrated, medium-scale, and large-scale integrated circuits, but today they're often implemented simply as very large-scale integrated circuits, VLSI. So given a single variable like x, we think about how rudimentary logic functions can be used to perform value fixing, transferring of that single variable value, inverting of that single variable, and then enabling. Given this input x, if we have the logic function equaling to 0, then the output's equal to 0. If the logic function equaling 1, then the output's equal to 1 no matter the value of x here. And we can also transfer the value of x. We can simply have the function equaling to whatever the x value is, 0 here as it came in 0, 1 here when it came in 1, or the function could be the inverted value of x. In this slide, we'll have a look at the enabling and disabling functions as a circuit to hopefully make it a bit clearer. Enabling permits an input signal to pass through to an output, and that can be seen here in the first circuit where we have a variable x coming in and enable. And if we were enabling, we would have this input enable to be 1, and then the output is going to be the same value as x. So if we get x equaling 1, then we have f equaling 1. And if we have x equaling to 0, then we have the f equaling to 0. The second circuit example that uses an OR has if enable is equal to 1, then the output of this NOT gate is 0, and then f will be simply the same value as x. If x is 0, f is 0. Whilst if x is 1, then f is also 1. Disabling, on the other hand, blocks an input from passing through to the output and replaces it with a fixed value. If we wanted the fixed value to be 0, then we would create a circuit something like this, where no matter what the x value is, since this en is equal to 0, then whether this is 1 or 0, the output is going to be 0. If we wanted the fixed value to be 1, we would use this second function where having en equaling to 0 gives a 1 here, and then no matter what the value of x is, whether it's 1 or 0, then we have f equaling to 1, because this is also 1. So 1 or 1 is 1, 0 or 1 is 1. Decoding is the process by which we convert an n-bit input code to an m-bit output code,
such that n is less than or equal to m, and m is less than or equal to 2 to the n.
And that makes sure that each valid input code word produces a unique output code. Circuits that perform decoding are called decoders, easy to remember there. And here we're going to call function blocks that are for decoding the n to m line decoder, remembering that the input code is n-bit and the output code is m-bit. So input to output line decoders. And we also have to make sure that it generates 2 to the n or fewer minterms for the n input variables. So let's do the most basic example. We have a 1 to 2 line decoder. That is, we have one input, and that input is called A here. This is the input. And then the output, which is m bits, remembering n to m. So this is the outputs. It's 2 bits. A, the input, when it's 0, gives D1 the same as A, so that will also be 0. And D0 is not A. If we have A equaling to 1, then D1 is equal to 1 and D0 is equal to 0. Slightly more complicated, but still should be understandable, is the 2 to 4 line decoder. In this case, we have the 2 inputs, A1 and A0, and we have the 4 outputs from D0 through to D3. On each one of these lines, that is for the unique input code 00, we have a unique output code 1000. There are no other lines here where the output code is the same as that output code on the first line. So each unique input code maps to a unique output code. So let's follow through for the simple case on the first line where A0 is equal to 0. And A1 is also equal to 0, then we get a 1 here, a 1 here, a 0 here, 1 and 1 gives 1, 0 and 1 give 0, 1 and 0 give 0, 0 and 0 give 0. So for the input of 0, 0, we get the output of D0 being 1, and then D1, 2, and 3 being 0. You could follow that through for each one of those cases as an exercise. Note in this case that the 2 to 4 line decoder is made up of 2 1 to 2 line decoders and 4 AND gates. So we've essentially repeated this 1 to 2 line decoder twice, and then we've also included these 4 AND gates so as to get our 4 outputs. On the previous slide, we showed the 1 to 2 decoder and the 2 to 4 decoder, but if we want to expand that to be much larger number of inputs and outputs, then we would generally do the same procedure and build backwards from the outputs. Each of the output AND gates will be driven by 2 decoders with their number of inputs either equal or differing by 1. And then these decoders are usually designed using the same procedure until 1 to 2 line decoders are reached. It is possible to modify the procedure in such a way that the decoders can have a number of outputs that's not equal to 2 to the n, just so long as
the number of outputs m is less than or equal to 2 to the n and greater than or equal to n.
Here's a decoder example where we want to go from 3 inputs to 8 outputs. So we have a 3 to 8 line decoder. So as I said, the first step is to work backwards from that number of outputs. We have 8 outputs, m equaling to 8. So we have 8 AND gates at the end. The number of inputs to decoders we have driving those output ANDs is equal to 3, n equaling to 3. And the closest way we could possibly split this to equal is 2 to 4 line decoder and a 1 to 2 line decoder. With a 2 to 4 line decoder, we have the number of output ANDs equaling to 4 and the number of inputs decoding the driving output ANDs equaling to 2. The closest possible split to equal would be 2 1 to 2 line decoders. Let's have a look at the next slide for the results. So we've taken 2 out of the 3 inputs and we have them inside this dotted line block where we go from those 2 inputs to 4 separate outputs. And then we take the third input, we pass that through a 1 to 2 line decoder, and then we combine it with the outputs from that first 4 to 2 line decoder block. Now the circuitry in here gets a little bit more complicated to actually follow through, remembering of course that where there's a dot means there's a connection between that input wire coming in and these wires, and where there's no dot then there's no connection at all. So this wire here goes up like that and then connects all the way along here, whilst this wire, which is actually connected directly to A2, connects to these AND gates down the bottom, where the value of A2 by itself would be reflected as enabling the outputs D4 through to D7, since A2 is directly connected to these 4 AND gates, and then not A2 enabling D0 through to D3, since not A2 is directly connected to these top 4 AND gates. And the outputs of the first 2 to the 4 line decoder, 4 outputs of that are connected to D0 and D4 for the first output, 1 and 5 for the second, 2 and 6 for the third, and 3 and 7 for the fourth. In this example, we're going to use what we learned previously in the 2 to 4 line decoder and the 3 to 8 line decoder, such that we can create a 7 to 128 line decoder. So for the entire circuit, we have 128 outputs. Therefore, we need 128 ANDs at the end, and we have 7 inputs to the decoders driving the output ANDs. The closest possible split we can think of is 4 to 16 and 3 to 8. And intuitively, when we look at this, we can see that we're going to be able to break it down into the 2 to 4 decoders. But just looking at this split, first of all, we have to add the inputs. So 4 and 3 gives 7. And we have to multiply the outputs. We have 16 outputs and 8 outputs here gives 128. Then for the 4 to 16 line decoder, we have 16 outputs, therefore 16 ANDs. We have 4 inputs to the decoders driving the output ANDs. And the way we can split that up is 2 to 4 line decoders. We have 2 plus 2 equals 4 inputs. 4 times 4 is 16 outputs. As an exercise, you could draw this up, but I suspect it would get quite messy towards the end when you combine all the outputs together. But it's just important to think about, given a number of inputs and a number of outputs, how to expand what we know about the simple case of decoders such that it can be used to solve a much larger decoder in the general case. Decoders can also have an enable as well. So remembering before we had enabling, allowing us to either use the inputs that are coming into that enabling circuit or to use a fixed value. So in general, we would attach that enable input, shown here, to M and outputs after the 2 to 4 decoder, such that we can enable that output or disable it. In the case where enable is equal to 0, then it's irrelevant what A1 and A0 are, what these inputs to the 2 to 4 decoder are, because enabling equal to 0 will leave you with 0 going into all of these AND gates, therefore D0 to 3 is going to be all 0. If we have enabling equal to 1, then whatever's coming out of the 2 to 4 decoder will be reflected in the outputs D0 through to D3, as they are for these 4 unique cases of A1 and A0. This type of circuit is called a demultiplexer, and in the next part of this lecture we will talk about multiplexers in more detail. If we wanted to implement a decoder with OR gates, such as if we were doing a set of odd parity functions, we could implement the M functions with n variables with a sum of minterm expressions, 1 n to 2 to the n line decoder, M OR gates, 1 for each output. The approach 1 would be to find the truth table for the functions and then make the connections to the corresponding ORs from the corresponding decoder output wherever a 1 appears in the truth table. And the second approach would be to find the minterms for each output function and then OR those minterms together. Let's look at an example of a decoder and OR gates, such as if we wanted to implement the set of odd parity functions of A7, A6, A5, and A3, where the outputs P1 equal to A7 XOR A5 XOR A3, and P2 is A7 XOR A6 XOR A3, and P4 is A7 XOR A6 XOR A5. On the left-hand side of this block, we have the 4 inputs. On the right-hand side, we have the 16 outputs. So we have a 4 to 16 line decoder. And then those 16 outputs are then connected into OR gates, where there is a single OR gate for each of the outputs, P1, P2, P4. So we would first find the minterm expressions. So for P1, they're listed there. And then inside this decoder, we would be turning the 4 inputs into outputs that we can OR together in this sum of minterms. And each one of these outputs would correspond to a minterm, and then we'd OR them together. We've ORed together, for example, 1, 2, 5, 6, 8, 11, 12, and 15 ORed together to give P1. So this is the circuit, and the question is this a good idea? And clearly, it's a bit of a mess because the complexity is really too high. It'd be much better to implement the functions with the XOR gates as it was originally specified. Also, something else that's not obvious here is that the sharing of the logic can cause 2 bits to be an error, which for this application is really not detectable. This is called a Hamming encoder, and you can read in the textbook for more information about that. Note also that even though it would be better to use the XOR gates, we really shouldn't share those in the implementation either. Selecting is the final topic of this part of the lecture. So selecting information is a critical function in digital systems and computers. Circuits that perform selecting have sets of information inputs from which the selection is made. They have a single output, whereas before we had multiple outputs, and there's a set of control lines for making that selection. Those control lines give some sort of code that allows the logic circuit to perform that selection, and these logic circuits are called multiplexers, and we're going to talk about them in the next part of the lecture.